So 21E is interpolation and extrapolation. Interpolation and extrapolation. And I just learned how to say interpolation like 2 days ago, so I'm probably going to stumble over both of those words. But we'll be alright. I was like... You guys got your stat box? Did everyone get the title? Okay, interpolation and extrapolation. Have you guys heard of those before? No.
Extrapolation.
Me, I was in the same boat where I heard of extrapolation, but I never heard of interpolation. So, sort of. I don't know if I would say opposite, but kind of in a way. Okay, so first we're going to get definitions for these words. So the important things are the poles. So the poles are the data with the lowest and highest values of x. So if we look at our data, our set of data, our information, the lowest value of x, the point that has the lowest x value is called the lower pole. The point that has the highest x value is called the upper pole, and we'll see that on a diagram in a moment after we're done defining these words. So we have the poles. I was thinking of like how we've got north and south pole, like the north pole at the top, south pole at the bottom. Those are poles. Now I've been talking about all week how we can use this stuff to make some estimates of what would happen based on our data, like for different values that are not a part of our data set exactly. So both interpolating and extrapolating are about that estimating. Now interpolating is when we estimate with an x value that is in between the poles. So we'll look at an example later, but if I use an x value that's in between the lowest and highest values, it's called interpolation. So I'm estimating that stuff. So when I estimate with a value that's outside of those poles, either less than the lowest value or greater than the highest values, that would be extrapolation. So extrapolating is when we estimate outside of the poles. So this diagram is straight out of your textbook, so I wouldn't say you have to write it all down, but it just shows us what this looks like. So we have a scatter diagram, we have our regression line drawn in that we can use for that estimation. All of our little points. The lowest x value is our lower pole. Again, the highest is our upper pole. So if we estimate with any x value that's in between, that's interpolation. So if I'm looking at a data that's in between and I want to kind of estimate what would happen using my line, interpolation. If I want to estimate with something that's really small or really big compared to the rest of our data, that's extrapolation. Now, when we take a look at these estimations, there are a few factors that kind of let us know how accurate our data is or our estimate would be. In general, interpolation is much more accurate than extrapolation. So if we are estimating with a value in here, it's going to be more accurate because it's in between the poles. It's still like in those values in the data set. But if we are estimating over here, it's not as accurate. So some other things for interpolation is that the accuracy depends on how linear the data is. How strong is that linear correlation. Now we know from a few sections ago that the strength is determined by the correlation coefficient R. So that has a higher correlation coefficient, then it'll be more accurate. Also, it's more accurate if the data is randomly scattered. So if it's not all bunched up, if it is random, then the accuracy will be greater. So the accuracy of the extrapolation also depends on that linearity, but if we are going to extrapolate, then we also are basing that on the assumption that the linear trend will continue beyond the poles. So it really does depend on the situation if that extrapolation is accurate or not. Well, like I said, in general, because we have to make the assumption that it's still going to go that way at the very low and very high end, so definitely not as accurate. So after this, we're going to take a look at an example and do a few different things with the same set of data for our example. This is data from your textbook. It's the opening problem on page 546. I think this is actually the example with the javelin throwing. I think I was confused when I said different example was. But we've got a bunch of athletes without names, A, B, C, and D, and so on, their age and years, and then the distance thrown. So if we look at the age range, the lowest age is 10, and the highest age is 20. So that gives us an idea of where our poles are. I use decimals to graph this and draw in the regression line. So 10 is like our lower pole because it's our lowest x value. And then 20 is our upper pole because it's the highest x value. Okay? So what I want you guys to do is use technology to find the regression line. So we want you guys to actually get out whatever calculator, keeping in mind that the age will be the x value or independent variable, and then the y will be the distance thrown. So I'll give you guys some time to figure out which technology you're going to use. I want you guys to find that line. This is what we did yesterday. It's really important that you kind of figure out what it is you're going to be using so that you can, feel confident on the test, because the expectation on much of it is that you use technology. Okay, so Miranda got one. I want to see what you got. Other people are getting.
I did it wrong.
I think something's wrong. I did it wrong the first time, but I had 3 people in my other class get the same answer, which is what we're going to have, so that's what we went with. So what do we get? Oh, go back to stat again, and go down to linear regression 4.
Oh.
Okay, now this is setting, but we have to fix this is right. Yeah, this is right. But you're supposed to see R here as well. Unlike my favorite signal.
Somebody has a calculator like that, and it shows like 4 instead of like an actual fraction. Oh, that makes me so angry. I'm trying to hang this out. Yeah, there's a lot. We want the frequency on or off.
Go back to linear regression. Okay. All right.
I found something.
Okay. What did Miranda? What did you get
For y,
for what's the a value?
the a is 3.38
So 3.29x,
Yeah.
and what's the y-intercept? It's negative
20.3.
20.3. So if you're not getting that, just double check that you're entering your data correctly. And then my advice for the upcoming test is just be very, very careful when you are entering your data.
Are you still not getting it?
Okay, then just leave your data in there and I'll take it out, okay? So that was yesterday. Now we have to interpret the slope and the y-intercept. So remember that slope is 3.29. So interpreting that, every year older the athlete gets, they're throwing about 3.29 meters further than the year before. Because that's like that slope is 3.29. So every year they're throwing it just a little bit further. Does that make sense? Like, 'cause we're going by years for our x value, so my slope every year is a 3.29. It's hard for me when you guys are like looking at your phones and not like looking up here. I don't know if you're getting it. Are you getting it? Okay. Now the y-intercept is the one that makes no sense on this problem. It's like the part of the example that is not a good question for this type of problem, but you will be asked it. But let's think about the y-intercept. What makes the y-intercept a y-intercept? It intercepts the y-axis, so what's our x value at the y-intercept? 0. So the reason why it doesn't make sense is that at 0 years old, they can throw negative 20. So I'm saying, like, it does not make sense with this particular problem. But when you are asked it, like I know there's one on your assignment, or I think there's one on your assignment that's like talking about hours. And so at 0 hours, you can see what was happening. So keep in mind that would be like when x is 0, and then you kind of comment on what's happening with the y for that one. All right, now we're going to use the same data. I'm not going to keep the chart up, but I am going to keep the graph going so we can use that as a reminder of the information in our charts. So how far would we expect a 14-year-old to throw? Is this interpolation or extrapolation? Now, I know we could use our graph to make an estimate, but we're counting like kind of strangely here by tens. So like this would be 15, 14 would be about here. And so I'm not getting something super accurate with my estimate using the graph. But what I can do is I can use that equation, which was 3.29, and I can put 14 in the x spot. So that'll give me a much more accurate answer than if I use the graph. Yes, the graph is good, it's a great tool, but with the lack of all of those different tick marks, it's probably better that we go ahead and use our calculator for that. You got it? Oh, okay. Well, we'll get to that later. So when we plug in 14 times 3.29 and minus the 20.3, we get 25.8 meters. So we would expect a 14-year-old to be able to throw the javelin about 25.8 meters. Now, is this interpolation or extrapolation? Interpolation, very good, because it's in between those poles. My lower pole was at 10, my upper pole is at 20. 14 is in between the poles, it's interpolation. Now, similarly, let's say we would try to figure out how far an 8-year-old would throw. We would do this the same way, but plugging 8 into the x value. Which I know you guys know how to do this, but just as a reminder, so that's about 6.02 meters. So we would expect an 8-year-old to not be able to throw it too far, about 6 meters. And again, that would be kind of hard to estimate because 8 would be like probably about here, and it's a little off here. So is this one interpolation or extrapolation? Yeah, extrapolation. And then on the next screen, we're going to talk about the accuracy or the reliability of these values. But are there any questions on how you can use the equation to make those predictions, those estimates? All right. So what do you think the reliability is of those estimates? Which one would be more reliable? The one about the 14-year-old or one about the 8-year-old? Which one's probably more accurate? The 14-year-old, because it was interpolation. So even though we made an estimate for an 8-year-old, it's not as accurate because it was outside of the poles. So about how old would a child most likely be if they throw 30 meters? If they can throw it 30 meters, about how old? How do we set this up? It's a little bit different than the other two because we're not given the age. We're trying to find the age. So is age on the y-axis or the x-axis? Wait. Yep, age is on the x. So we're looking for the x. So we have to plug 30 in where the y would be. So 30 equals 3.29x minus 20.3. So if we subtract 20.3, and then we have to divide, we have to add the 20.3, and then divide by the 3.29. So about 15.3. So in order to throw 30 meters, they should be about, 15 years old. Any questions?
Can you just how you're doing that thing with the graph, you just go over and down? That's kind of how I found it.
I think for this one it would work. Yeah, for that one. But do you see what I was saying for the other ones? When because this would be 2.55, 7.5. It's not quite as accurate when it's in the middle. But for that one, absolutely. So it's one of those things where I'm really glad that was brought up. Sometimes the graph is completely fine. Sometimes it's better to use the equation. You can kind of decide, judge for yourself on the accuracy. If you're kind of wavering between those grid marks, that might not be the best way to do it. 30 was right on there, so that works out well. Okay, that box has two parts. So the first part is how will you remember the difference between interpolation and extrapolation? Yeah, in is in in between. Interpolation is in between. Extrapolation is out, maybe exterior, outside. Also, interpolation, remember, is more accurate than extrapolation. This other question is, well, what type of technology will you use to calculate the correlation coefficient and the regression line? Because there's definitely some problems on your test that we want you to use technology, so you should know what you will be using. You should be able to practice with it. So make sure you practice with whatever type of technology you plan on using. That is it.